The exam 2 study guide is on the 8th week Tuesday. So you can click on the link, then you should be able to see the study guide. We covered chapter 5 to 7. I was going to cover chapter 8, but I think you probably need some time to prepare. So we're going to lift the chapter 8 to the next week. Chapter 5 to chapter 7, there are a couple of things that you need to know. We talk about the diffusion, which is chapter 5. There's a fixed law, the first and second law, that you need to know how to solve those problems. So the first law assumes the grading, the concentration grading during diffusion is a constant. It's a constant rate, which is called the flux. The second law is a non-constant, is you have to solve a PDE, which we don't require you to know how to solve it. We just give you a solution. The solution requires you to use an error function. So if you do the homework chapter 5, then you should know how to solve the problem with the error function. A lot of time you have to do the interpolation to find either the error function value or the z value. So that's the part that you should know before you come to the exam. Make sure that you go through some of the example of those things. The last part of the chapter 5 is about the semiconductor diffusion problem that give you the depths of the deposition and concentration at certain depths. Then it will ask you how much time does it take, what is the temperature, etc., etc. And some of the homework problem about that as well. You should review those things. Then the chapter 6 is another important part of the materials, which we start to talk about the mechanical property of the material. The mechanical property of the material, we are looking at the metal first, and you did the experiment 2 weeks ago, which is the tensile test. There are more tests after this, so the next week we're going to cover several different kind of tests. There's one test we haven't started yet, which is the hardness, and that is very simple. We just need you to know about how you can convert the hardness to a tensile strength, and also get an idea how to do a hardness test. The tensile test is the one that you should spend more time to look at that. Definitely, you're going to have one problem about the stress and strain curve. So I will probably just give you a curve and ask you to identify several things. And sometimes I might just give you some information that you have to solve the problem, use the graph. So you need to know how to find the Young's modulus, which is the slope of the linear region. You also need to know how to get a stress and strain. And if we specify a stress, can you identify whether it's in the linear region or if it's in the plastic deformation region? And we might just give you a strength. They ask you to find what is the strength at that point. Also, this is also related to the true stress and true strain. When you do the true stress and true strain, you are using the actual area to do an actual strength, actual length to do the stress and strain. So,
Professor?
Yes.
You sound muffled, like something's covering your mic.
Oh, would this one better?
Yeah.
Okay. So, where I'm talking about the stress and strain. So, if you are doing an engineer stress and strain, and then you are using the original dimension to find the strain. If you're doing a true strain, then you are using the actual diameter to do the strain. The actual diameter will keep on changing while the specimen is being under the load. So when you pull the object, it will become smaller and smaller, so it just keep on changing. It's different from the engineering. It's different from engineering. Okay, so there's some formula in your textbook. By the way, there's a formula sheet in this page that you can download it and get familiar with the formula sheet. This is just a copy from the formula on the back of your textbook. That is the formula sheet that I will give you in the exam. The next thing is that also there's a ductility. So when we do the ductility, we look at the percentage of elongation. We can also look at the percentage of the reduction of the area. So these two are the way that we can describe what is the ductility of the material. If material has less than 5% of the elongation ductility percentage, that means the material is brittle. It's just a general guidance to tell us how brittle or how ductile a material is. And more than that, we just say, well, this is not so brittle. It's probably is a more ductile material. So that is how we distinguish these two. Then the chapter 7 is about the dislocation. The dislocation is looking at when the object is under a load, how would this object fail? What direction and what plane will the object fail? And this is related to the dislocation mechanism. You should know there's two different dislocation. One is the H and one is the screw. The difference is depends on the direction of the dislocation and also the direction of the H vector. So that is the main difference. And there's a drawing in your textbook to show you the difference. And then you can take a look, get an idea of what is the difference between these two. The slip system and the slip system refers to the slip plane and also the slip direction. The slip plane and slip direction are the most packed plane. The PD is the highest, and the most packed direction, which the LD is the most. So how do you find the PD and how do you find the LD was the topic that we mentioned in the last exam, but you should know how to find those things. When you look at the PD, the planar density, you're looking at how much of the area covered by the atom over the cross-section area of the unit cell. And direction is looking at the line. And if you look at the direction and just see how much of the percentage of the line being covered by the atom, that is the linear density. So these two density, these two are the slip system. In this one, you have some calculation about the Berger factors, which is the unit vector for the qubit system that you have a BCC, FCC, HCP. Each one of them, because they have a different direction of the slip, so they will have a different formula to calculate the Berger. Berger vector length is related to the lattice length. The lattice length is the A. The A represent the dimension of the qubit system. Then the next topic that you did, if you did the homework of chapter 7, then you know there's some question about the resolve the shear stress. So what is the cause of that? Well, the cause of that was because the crystal system under the tensile stress, remember tensile stress is the stress acting actually, but it doesn't break actually. It will break in certain plane at certain direction. So if that is the case, then you have to use this one to find what is the shear stress to make the material break. And one of the challenging part of this kind of problem is to find the angle. So today we're going to show you one of the example, and in your homework you got more question that you can do the practice. So I'm going to show you the example by using the practice problem. The last one is also an important part of the chapter 7, which is about the strengthening mechanism and heat treatment. There are 3 different mechanisms to strengthen the material, which are the solid solution, and um, the strand hardening, which is also known as the cold work hardening, and the other one is the grain size reduction. So 3 different ways that you can make the material, the metal material, to be stronger. And when you have this mechanism, look carefully for cold work, they have some calculation problem related to the cold work. You have to look at the graph to find a solution. For the grain size reduction, there's an equation that relate the grain size with an exponent n with a constant k. So based on the material and based on the order, then you can find out how much time does it need for the grain size to be reduced. So that's the problem related to this chapter. So these are the things that you should know. Okay, any question about the topics? Then let's look at the practice exam problem. Here I list the several problems over here. It's not only limited at this problem will be show up in your exam. I will be probably give you similar format as the last time. You might have some multiple choice questions which ask you about the concept of the book. And how come sorry, I just go to the wrong place. Okay, yeah, I might give you some of the, this is not, some of the multiple choice question test your understanding about the concept, and the majority of the problem will be the calculation. So
Professor, you're muffled again.
what about now?
No, you're good.
I think it's the angle that I put my pad. Okay, so as I said, some of the question will be multiple choice questions. Some of the question, the majority of the question will be the calculation. So I'm going to just work on some of the calculation like this one here. And I'm going to use my note to write something about the answer for these questions. All right, let me open my OneNote. Wow, it doesn't work out. Huh. Oh, it's right here. Okay, so here the simple question. The first question asking about the difference between the edge and the screw dislocation in terms of the direction of the motion and the shear stress direction. And you sketch the fact of the edge and the dislocation of the surrounding crystal lattice. So all these answers are in your textbook. Let me just open one of them, which is about the dislocation. I think I just showed that here. So here are the picture of these two different dislocation. So on the top is our like edge dislocation. At the bottom, which is the screw dislocation. The difference is that the shear stress is the blue color, is the green color one, the tau, and the direction of the motion is the red color arrow. So you can see the direction of the dislocation always goes to the right. However, the shear stress, you might go horizontally, which is parallel to the direction of the motion. That is the screw dislocation. If you go perpendicular, then is the, oh, sorry, that was the edge. I was said it wrong. So the edge is parallel. Edge is parallel, which is this one here. This is the edge. And screw is the perpendicular. So this one is the screw. And when we say this Perpendicular, we're referring to this direction and this direction. So this direction and this direction. They both make the material goes to the right, but the direction of the dislocation and the shear stress are in a different angle. Okay, the next problem of the review question is not this one here, sorry, is this one here. So this next question is about chapter 5, which is about the diffusion. We have two different diffusion. The first one is the first law, which assumes the diffusion happen in like a constant. The diffusion rate is a constant. The second one, the diffusion rate is a time dependent variable and also the position dependent variable. So it's a partial differential equation. And since you haven't know how to solve that, we would not ask you to show us how to solve the problem, but we give you the solution. You have to be able to use the solution to find the result. So how do we do that? How do we apply that? We're going to use this example. So they tell you there's a thick wall pipe. So that pipe is so thick that you don't have to worry about the diffusion happen on the pipe. The diffusion actually happen in the membrane inside of this pipe. So let me just draw a picture to show the idea of this. So here you have a pipe. The pipe has certain thickness, and this pipe certain distance long, and this is the pipe go all the way to the end. Inside of the pipe, then you have a thin membrane. Okay, this is a membrane. This membrane is an iron. Okay, they give you the thickness of the membrane, which is here. This is the thickness of the membrane. This is a 0.001 centimeter. The diameter of this pipe is given as 3 centimeter diameter, the inner diameter, so that's 3 centimeter. And they also tell you what is the thing inside, that nitrogen that you have inside. So you have a nitrogen here, and the nitrogen is going to diffuse to the other side of the membrane. Okay, now initially on the left hand side that you have 5 times 10 to the 19th of nitrogen atoms per cubic centimeter. On the right hand side, initially that you have the nitrogen to be 1 times 10 to the 18 atoms and centimeter cube. Okay, so that is the situation they give you. And they also tell you if you are using a continuously replenished gas, when you continuously replenish the gas, that means this one is going to be the constant flux, which you are going to use the fixed first law. So what is the fixed first law? The fixed first law give you the flux is equal to minus d times change of c over change of x. The change of c represent the change of the concentration. The change of x represent how much of the distance that you are allowing the atom to do the diffusion. In this case, the delta x represent the thickness. So this one here is the delta x. And what is the change of the concentration? Well, the change of concentration is the concentration of this one and this one is the difference of these two. But then you also need to know this D over here. So what is the D? Well, the D is the diffusion coefficient. Are we given with that information? So you read the problem, they also give you that over here. The diffusivity of the carbon is this much. So that is the diffusion coefficient, the D. So now you have all the information. All you need is just put it all together, then you can find the answer. So let's just write it down. This will be 2 times 10 to the -7 times the change of C. So what is the change of C? So the change of C is going to be the later one minus the previous one, which is 1 times 10 to the 18 atom cubic center minus 5 times 10 19th atoms divided by cubic centimeter and divide by the change of the distance, which is the thickness, that's at 0.001 centimeter. The unit for this one here is given the centimeter square divided by second. All right, so if you do the calculation, you will find out 1 times 10 to the 18 minus 5 times 10 to the 19 give you a negative number. So what does that negative number mean? Well, it's positive, but you put a negative in front of that, simply just meaning the concentration is getting to be smaller and smaller from the left. It's just going to the right. So if you put the things in there, you're going to get the result, which is going to be 1.96 times 10 to the 16 atoms divided by centimeter square times second. This is the answer for the flux, okay? But the question is not asking you about the flux. Look at what the question is asking about. Well, we wanted to determine the total number of nitrogen atom pass through this membrane at 700 Celsius. Oh, by the way, I used the wrong number. I should use 4 times 10 to the 7. So here, I was using the wrong number here. So let me change this one. This should be 4 times 10 to the -7. This coefficient depends on the temperature, okay? They just tell you at a 700 degrees Celsius, the diffusion coefficient is 4 times 10 to the -7. In chapter 5, there's also a section and the equation tell you how to find that. So they want to ask you about the total number of the atoms and in one second. Okay, so in 1 second. So how do you find the number of atoms in 1 second? Well, you look at here the flux. The flux meaning how many of the atoms pass through centimeter square times time. So if I multiply this one with the area, multiply with this one with the time, which is 1 second, I will be able to find out in 1 second how many atoms will pass through this membrane. But what is the area? Well, the area is this area here. So you got a diameter, you can find out the area. So the area in this case is going to be pi times 3 centimeters squared divided by 4. So it's pi d squared divided by 4, which is the area of the membrane that will have the nitrogen to diffuse. Time is 1 second. Then you multiply them together, you can get the total number of the atom pass through that in 1 second, which is about 1.39 times 10 to the 17 atoms. Okay, so any question about this? All right.
Uh, real quick on this one, we have the from the formula sheet, we have flux is J equals M over AT. We just solved for J here using fixed first law.
The J by definition is M over AT, which A is the area, T is the time, and N is the number of the atom. So that is the definition of that. And then how do you find that? Based on the fixed first law, that is this equation. So you can say J equal to M over AT, and it's also equal to minus D times delta C over delta X if this is a steady state situation, which is this case. If you're looking at the non-steady state, now J still had the same definition, but it's not a fixed number, it's the function of time and position. So that would not, that equation to find the solution will be different. But that N over AT is just give you the definition of the flux.
I see how you used fixed first law here to get J, and I think I'm just getting a little mixed up here at the end, where you turned it into, where you multiplied by area and then times 1 second.
Okay, because the problem said, we specify, I'm asking for the total number of nitrogen atom, not the flux. The flux meaning in a cross-section area, how many the flow rate of the atom. So if you take a one centimeter square of the area and you have 5 atoms pass through in 1 second or 10 atoms in 1 second, that is the flux. But I wanted to know, say, this is an area, I just need to know in like 10 seconds how many atoms actually flow from the left to the right in total. That is not flux. Okay, so how do I get the number of atoms is the point. So here you have the flux is atom divided by centimeter square times second, which is the area in time. If you multiply with the area, you multiply with the period of time, then I would know how many atoms actually pass through the membrane.
Okay. Yeah, I think that's good. Having that J equals M over T, it seems like you used fixed first law to... Sorry, go ahead.
Yeah, sorry. You're using so we're actually using the definition of this. We try to find M. This is what the problem try to find. We try to find M. I'm not trying to find, like J. You got J, but I want you to find N. So how do you find N? You have to multiply the area, multiply with the time to get the N.
Yeah, okay, that's good. Thank you very much.
Okay. All right, so this is only in the first part of the problem. The second part of the problem is that they say, well, what happened if the nitrogen of the high concentration, which is the left-hand side, they do not continuously replenish that. They just start with 5 times 10 to the 19 and put a membrane in between, and on the right-hand side is 1 times 10 to the 18th. And what happened afterwards? Well, if that is the case, the diffusion will be continuously happening until both sides are going to be the same concentration. So the answer for this, the part B, is it will continue to diffuse until the both sides have the same concentration. So that diffusion will continue until they both sides have the same concentration. But when you have the same concentration, doesn't mean the atom doesn't move. It just the atom move to the right and the atom move to the left is going to be the same number. So the rate is the same, and you don't see the difference. The concentration will keep the constant on both sides, and it's going to be the same number. So that's what that means about the diffusion of the problem B. Let's look at the part C. Now, part C, it tells you you have a 0.1% carbon steel. We wanted to strengthen the surface through a carbonizing. So you use carbon to strengthen the material. You need to diffuse the carbon into the steel. This process is a diffusion, but this process is not going to be the fixed first law. You have to use the fixed second law in order to solve this problem. Now, for the fixed second law, things that you need to be careful is, if you look at the equation, let me write that equation here. Let me get some small space from my note. So, okay, I'm going to get more space here. Let me write down the second law. The second law equation is like this. Okay, so the thing that you need to be careful is that what does all these symbol means, all these symbol that you have in this equation. The X represent the position, is the position that you look at of the concentration that you're looking at. So C represent concentration. So Cx represent concentration at position X. X is the position. So let's say you have the steel at here. This is the steel. And you put a carbon on this surface here. These are the carbon. And you want to diffuse the carbon into the steel. Now, depends on the distance, the concentration that diffuse into the steel will be different. So here is the position I try to find. What is the concentration at this point is going to be the Cx. So this is the concentration at that point. And what is the Cs? Well, the Cs is the surface concentration. It is the concentration right at here. And sometimes, well, most of the time, this is going to be what is the concentration on the surface of the steel. Okay, and this you also have another one which is the C0. So the C0 actually represent initially in your steel what is the concentration inside of the steel. So it's the initial concentration in the metal. Okay, so the D here represent the diffusion coefficient, the T represent time. So normally if we write small t, it's time. If this capital T, it will be the temperature. So here is the problem that you need to solve, and let's see how we can solve this problem. Let's go back to the problem and get those information. Let me just shrink this one so we can see both top and bottom. So read it carefully. 0.1 carbon steel. we want to strengthen the surface by this process, and the gas has 1.2 carbon in contact with the surface at the temperature. They didn't tell you the temperature, but they tell you the diffusivity of the carbon steel is 2 times 10 to the negative 7. So just by looking at this statement, what kind of information do you have? What does the 0.1 means? So 0.1 is the initial concentration. The 1.2 is the surface concentration because it's in contact with the surface. So this one is 1.2. Okay, and they give you the D. So the D over here is going to be 2 times 10 to the negative 7. And what else? They say we want 0.45% of a carbon at a depth of 0.2 centimeter. So that tells you X is equal to 0.2 centimeter. And what does 0.45 means? That means the Cx is equal to 0.45%. Okay, now you got all this information. What you need to do is to solve this problem based on this information. And how do you put this together? Now let's just write down, put everything into the equation. So the Cx is 0.45. My C0 is 0.1. And at the bottom surface is 1.2. And the C0 is 0.1. They all are in percentage. I can kind of cancel it out, so I didn't write percentage at here. That equal to 1 minus ERF of something at here. So what is the thing we don't know?
Time.
Time, we don't know time, and then we want to find the time. So because I don't know the time, I'm going to say this is some kind of symbol here, which is Z. This is the parameter in the error function. We put the Z over here. Later on, we're going to deal with the Z. So I want to find the result of this. And this should be very simple because you can divide these two numbers, this two, and to get a number. And then you are going to find the ERF of Z equal to a number. That number came out to be 0.6818. Then what are we going to do? Well, then you're going to use the error function table. If you don't know about this, that means you didn't work on the homework yet. So you should definitely work on those problems because this is one of the problems you're going to see in your exam. So you look at the table of the error function, which I will provide to you.
I was going to ask if we were given a table for that.
Absolutely.
Okay.
All the table and the graph will be provided. So here, I just list the partial of that. So you just need a partial of that. So you have the table have the 0.7 of the Z and 0.75 of the Z, and they give you the value, which is 0.6778, give you another value of 0.7112. Now our value, the error function value that we got is this value, which is in between these two.
Do you mind if I ask real quick? You have the ERFZ equals 0.6818. Is that something you calculated, or is that something that was given?
I calculate on this one here.
Oh, okay. You
So
solved.
you put it, yeah,
Got it.
solve,
Got it.
make an ERF to the left, right? And 1
Mhm.
minus ratio of that number will give you that.
My bad. Thank you.
Yeah, and then we want to find this value here because this value is the Z, and this value is actually equal to your X over 2 square root of D times T. So I need to find this question mark here. And you have to do the interpolation. So you kind of assume everything changes linearly, and then you do the interpolation. So if you still not know how to do the interpolation, look at the example in the textbook and do some homework problem. Here, it's very simple idea. So you say, oh, from 0.75 to 0.7, and I have a distance of this much. And then now I'm changing to this one here, and the difference will be these. So you take the difference of the number of the ERF, 0.7112 minus 0.6778. This will give you the difference of 0.75 minus 0.7. If I change it to the 0.681A minus 0.6778, then that should give me the ratio of the question mark minus 0.7. And you take the ratio of these two, then you solve for the question mark. And let's just say this is the Z, and you solve for the Z. Okay, I'm not going to spend time to show you how to solve this, but if you solve this, you're going to get 0.7060. Which means if you put 0.7066, then you got the value of the ERF function to be 0.6818. And that means this one is going to be 0.7060. And then what do? Well, then you put x equal to 0.2, and you put d 2 times 10 to the negative 7. You solve for t. Okay, and the t is going to be in what unit? Well, in this case, the diffusivity is in centimeters times second, so the result is going to be in second. So again, I will let you try this because we don't have time to go through all the details how to solve this. This will be t equal to 1.00313 second. If you convert this one into hour, that will be 27.9 hour. Okay, question about this? Okay, let's look at the next one. So definitely look at the fixed law. It's going to be one of the questions in your exam, at least. All right, the next one that we're looking at is the chapter 6. The chapter 6, the main thing is the tensile test. And you already do the lab. I hope that you understand all this terminology that we mentioned in here. We want you to sketch a stress strain graph. And you need to label the yield strains, optimal strains, break-in strains, elastic plastic region. So if we draw the picture, this will be your stress, this will be your strain, and this will be some kind of curve for certain kind of material. Different material might have different curve. We also tell you how do you tell which one is more brittle, which one is more ductile, right? So make sure that you know how to do how to distinguish them. So the yield stress normally is the stress that you are start to have the plastic deformation. So what we normally do is we will do a 0.2% yield stress. So this one is our yielding stress. This is a yielding stress. The ultimate stress is the highest peak, so this will be your sigma U or the tensile strength. So this is the U. This stress here is the breaking stress or the fractal stress. So this one is the sigma B here. Elastic and plastic region, then you just look at the curve, just say, oh, this is the elastic region. And starting from here, you're going to have a permanent deformation. This will be the plastic. This is important because once you identify these things, there's another two property related to the elastic and plastic region, which is the resilience and also the toughness. The resilience represents the area under the linear region. So this is the resilience. The toughness represents, the toughness represents the area of the total. So it should be, should draw in this way, it should be the area including here to here. So that's the total area. Okay, that is the toughness. And what is the modulus of elasticity? It is the slope at the linear region at the elastic, which is the slope of here. This is also known as the E. It's the Young's modulus. Okay, and you can also find out the percentage of elongation, and you can also find out the percentage of the area reduction. And that is going to base on the strength. If you are given with the original length, then you can find out each one of them. So these are the things that you should know how to solve it by looking at this graph. So here I'm kind of use the graph to explain different things, but I can give you like a graph of an experiment, ask you to identify those things as well. Or I can give you, you know, a graph that that you find out some of the value based on the graph. So make sure that you understand that, and which is part of the of your lab. I think that you should know this. Okay, the last one here I want to show you, which is about the resolved shear stress. The equation of that is right here. So here, these are the two things you need to use in order to solve that problem. This is the picture of the tau of the resolved shear stress. Equation is this one here. This equation depends on two angles. As I said, the most important thing is how do you find those two angles? You have angle of phi, you have an angle of lambda. Now the lambda is here, phi is here. So lambda is the angle between the stress and the slip direction. This phi here is the stress and the normal to the area, normal to the slip plane. Okay, so that is the, so I think this one is easy to find. This one sometimes is harder because you have to know what is the direction normal to the slip plane. The direction normal to the slip plane is sometimes harder to visualize it. Then you have to see what kind of problem that you have. So here is a picture that shows you the example. If you have a plane, which is the yellow color one, so that one is the slip plane, and that plane is 110. Then the direction normal to the plane will be what? Which will be this direction. And if you look at that direction will be the direction like this one here, from this one to here. And what is this direction? Then you look at, well, this one at this point here is what? It's 1, 1, 1, right? And what is this point here? This one is 0, 0, 1. So you take subtraction of these two, you got the direction of that, which is going to be 0, 1. Wait, this is 1, 1, 1. So this is 1, 1, 1. 1, 1, 1 minus 0, 0, 1. That is 1, 1, 1, 0. So the normal to the slip plane direction is going to be 1, 1, 0. And the direction of the applied stress is here, the 0, 1, 0. And the slip direction, they also give you, which is negative 1 and 1 and 1. You need to get all these directions in order to find the angle. So once you have all these directions, and then you can find the angle by the 7.9 equation. Let me show you how to use this. Let's say you want to find the angle between this one here, which you try to find the angle of phi. This angle is the angle between the applied stress, which is this one here, 0, 1, 0, and the normal to the slip plane, which is this one here, 1, 1, 0. And you just treat this one to be the U1, U1, V1, W1, then U2, V2, W2. So put everything in the equation. So this one is equal to up cosine. And you have 0 times 1, 0 times 1, plus 1 times 1, plus 0 times 0. That's the U1, U2, V1, V2, etc., etc. At the bottom, you're going to have the U1 plus V1 square plus W1 square, right? So that will be 0 square plus 1 square plus 0 square. Multiply with 1 square plus 1 square plus 0 square. And then you solve this. Then this will be the angle of the phi. Similarly, you can do the other one. Okay, the other one will be the angle between the 1, negative 1, 1, and 1, and the 0, 1, 0. Okay, so let's go back to the problem. The problem is actually very similar to that. Now we're looking at the situation, a single crystal structure. They tell you tensile stress direction. Okay, this is the direction of the sigma. Direction is 0, 0, 1. And slip occur on this plane. So the plane direction is the slip plane is 1, 1, 1, but they don't tell you the direction no more to the plane. You need to find this. And the another one is that the direction of the slip direction is negative 1, 0, and 1. They give you this one, the magnitude of this one is 1.1 megapascal, and you want to find what is the tau of resolve the stress. So how do we do this one here? Well, you have to find the angle, right? So for this one here, then you can get a lambda. Lambda is up cosine of that equation. So that equation is that you use a negative 1, 0, 1, and 0, 0, 1 to do the calculation. So 0 times -1 plus 0 times 0 plus 1 times 1. At the bottom, you're going to have a square root of -1 squared plus 0 squared plus 1 squared multiply with 0 squared plus 0 squared plus 1 squared, and that gives you the length. The question is, how do you find the slit plane normal direction? So if you look at the cubic cell, the 1, 1, 1 direction is the direction at here. This is the 1, 1, 1 plane. Sorry, this is not direction. This is 1, 1, 1 plane. They all connect to the peak point of each one of the unit number. And the direction is going to be the direction from this point to this point. So it's actually from this point to the diagonal of the other side. Okay, so that direction is actually the 1, 1, 1 direction as well. So once you have this, then you can also find this angle. This angle is going to be similar to that. I'm not going to write this, but if you do the calculation, you're going to find that lambda is going to be 45 degrees. The phi over here, use this one here, and the other angle, the other direction will be 0, 0, 1. Then you will find out this angle is going to be 54.7 degrees. Then you put this angle and into that equation, you can find the result. Okay, so any question about this problem? You also have some of the question in your homework, and you can use this as an idea, but I just want to show you how to use those equations to find the angle. Okay, the last question here is about the co-work. Okay, we told you there's 3 different ways you can strengthen the material. Co-work is one of them. If you wanted to use the co-work to strengthen the material, and there's some graph that you have to find in your textbook. I believe that's the figure 7.6 or something like that. That figure gives you the figure that related to the percentage of the co-work with the strength, the yield stress, and also the percentage of the elongation, percentage of the EL. So 3 different graphs. You're going to use those graphs to find the result. So let me see how to work on this one here. Okay, so what is given information? They give you material is the steel, 1040 steel. They tell you the minimum tensile stress is 865. So let's just write down those information. Is 1040 steel. And the tensile strength, the minimum, is equal to 865 megapascal. The ductility, at least 10%. So the percentage of the EL has to be greater than 10%. Okay, and the final diameter is 6 millimeter. That is what we try to create. But you are given a material which has a diameter is 7.94 millimeter. It's this 1040 steel, and it has been co-worked. So the percentage of the co-work is equal to 20%. And how do you create from this one to this one here? Based on the specified requirements. Okay, and they also tell you here, if you put too much of the co-work, then this steel might break. And the limit is 40%. So you cannot give the cold work more than 40%. Okay, so how do we do this? Well, we start with the steel like this, which is 7.94 millimeter. I want to create a steel like this, which is only like 6 millimeter in diameter. The easier way that you do is just simply just press it into to extrude it to make it to be a smaller, right? You just do a cold work, then you can create that. So if that is the case, then we can find out how much of the cold work that we did. If that cold work doesn't exist, doesn't over the 40%, then that's just the simple thing that we have to do, right? So if we do cold work to change size from 7.94 millimeter to 6 millimeter, let's find out the percentage of the cold work. That is equal to A0 minus A final over A0 times 100%. And what is my A0? A0, you start with 7.94. So it's 7.94, it's the diameter squared times pi divided by 4. That is the area of the initial. My final is going to be 6 squared divided by 4 again here. And my initial again is going to be pi 7.94 squared divided by 4. And you multiply with 100%. Now you can see a lot of things can cancel out, the pi and 4. You can cancel them out. Then the rest of the thing is just a bunch of number. Then you do the calculation. It turns out this one to be 75.1%. What does that mean? That means if you simply just do the cold work starting from 7.94 to 6 millimeter, you have to do 75% of the cold work. And which the probability tells you, if you do more than 40%, it's going to break. That means you cannot do it in this way. It's not a possible way that you can create that, just simply do one-time cold work. So the strategy to solve this problem is this. Do a cold work to shrink, to reduce the diameter within the percentage of a cold work less than 40. You don't want a cold work to be greater than 40. So you kind of shrink the size once, and it's not go to the 6 millimeter yet. Because if you shrink it too much, it will over 60%, 40%. So, and then what? Then you do the annealing, the heat treatment. By annealing. The annealing includes 3 processes. It's in your book, chapter 7. You have a recovery, you have a recrystallization, and you have another, I think, is the strengthening. So there's like a process, and the grain size growth. So the last process is the growth. So you let the material heal after the cold work, then you can do another cold work. So you reduce that again to be the 6 millimeter. Okay. So you can pick a numbers as long as the cowork is to be less than 40. So I tried this one before. I just do like a, so I try do 30% of the cowork. And I want to find what will be the diameter that I need to reduce. So if I do 30% of the cowork, what will be the diameter? Let's say the diameter 1. Then how do you solve the diameter? Well, it's the same equation like this, but you're going to put 30% here, and you that equal to pi times d squared over 4. I'm going to eliminate pi over 4 because it will cancel out. I just need to write the diameter square. So I start with 7.94 square minus d1 square over 7.94 square. And I solve for d1. That is the diameter I'm going to do for the first cowork. And the cowork is 30%. So it turns out if you solve this, it's going to give you 6.96 millimeter. So that means you do 6.96 millimeter of the cowork, then you're going to reduce the diameter from 794 to 696. Then you have to check. Then you do, so this will be the first step. The second step is do the heat treatment. And the third step is going to do another. All right, but this is not the end, because you also have to check if you do the cowork from 6.94 to 6, would that also go over 40% or not? If it's not, then it's okay. So let's find out what's the percentage of cowork if we do the reduction like this. Again, you can eliminate the pi over 4, 6.96 squared minus 6 squared divided by 6.96 squared. And that is the percentage of the cowork of the second stage. And let me find the result of this. I didn't calculate this one. Okay, it turns out this percentage is 25.7%. And that's less than 40. That means this is okay. So you can do in this way, then you can create the material that you want. Okay, so these are the problems that I listed in the practice exam problem. Just wanted to make sure that you do the homework and understand how to solve this kind of problem. Any question about this?